So the shaded region here R is bounded by the graphs of functions f and g, and you can see the g is the function above and f is the function below, as shown in the figure. So we need to find the area of that region. And so we need to find the intersection points. It's nice that the graph has that label, 3, 3. And we will do the integral from 0 to 3 of the upper function minus the lower function. And it is okay, and you would get full marks if you wrote g of x minus f of x instead of writing x plus sine pi x minus x squared minus 2x. So on the exam, they'll be looking at this, they'll be aligning a mark. Do you know that it goes from 0 to 3? Do you know that it's one function minus the other function? And it doesn't matter which way you write it. So this is simpler than writing out the actual equations. Now, when you go to type this into your calculator, okay, then you have to, of course, put these functions in. And some things we can do with our calculator. So I'm going to open up our calculator here. I'll make here. You can write down that answer so you have it. So especially in these questions that, if they have an A, B, C, and D, you're probably going to need to use things more than once. It might be helpful to type in the equations separately. So I'm going to go to y equals, I have it off to the side here, you can't see it right now, just so that I can see the equations. G of x was x plus sine pi x so I wrote x plus sine pi x in here, x squared minus sine x. My calculator is currently in radians. None of your derivatives don't work in degrees, sorry, and I switched it back to radians. So now I've got y1 in there, y2 in there. If I hit my graph, I see that same graph, a part of it, and we see the shaded region there. Now, if I want to find the area between these two curves, I can go to math, and I can go to number 9, the integral, and I can go from 0 to 3. And then here, instead of writing it all in, since I have g of x in y1, I can just type y1 instead, and I have f of x in y2. I can type that in instead with respect to x. And again, now my equations are in my graph, but I didn't need to retype them into my calculator. I didn't have to worry about, oh, I made a typo. I can double check it once to make sure that my equations are written correctly there, and then I can use those equations again. The region R is a base of a solid. Okay, for this solid at each cross section perpendicular to the x-axis. So as soon as I read that perpendicular part, I like to draw a line to say, okay, those cross sections are traveling this way perpendicular to the x-axis. So again, I'm going to be going from 0 to 3. Is a rectangle with height x and base in the region R. Find the volume of the solid. Show the setup for your calculations. Again, we're going to go from 0 to 3. I'm going to color code that. I have a rectangle. I'm going to put green brackets there. That's my length, or the base of my rectangle. It told me the height was x, so you see I had multiplied by another x there. Base times height, whatever you want to call width times height. And again, I can type this into my calculator. Now, do you see that this is very similar? And I'll put the answer up. You can write it down. This is very similar to what we just typed in. Right? We just typed in y1 minus y2 dx, and now we just have this extra x. So in your calculator, newer versions, you can use the arrow keys and highlight it. Okay? If you don't have the newer version, you can go second, enter, and it goes through everything that you've retyped. So what do I need to do here? I need to insert, above your delete button is an insert button. I can insert a bracket and put another bracket there, and then put another x. So now it's multiplied together, push enter, and I get my 7.705. So again, some shortcuts that you can see on your calculator here. Little things like this are very helpful on the exam. Write, but do not evaluate an integral expression for the volume of the solid generated when the region R is rotated about the horizontal line y equals -2. So here what I like to do, I like to draw my line y equals -2. I know that I'm rotating around that. And with my disk method and my washer method, I'm going to have a big radius and a small radius. So on my graph here, I'll do it in purple. I'm going to pick this point. That's my big radius. And in green, that's my little radius. Now, depending on what you're rotating around, figuring out those big radiuses and small radiuses are not hard, okay? But my big radius in purple, does it make sense that from here to here is actually my function g of x? And then I'm going to need to add 2 to that. The same thing's going to happen with my little radius. It's going to be whatever f of x is. And sometimes it's easier to imagine this by taking a point like there's, oops, sorry, that's not the point I want. Taking a point above the x-axis is easier to see it because you're going to get f of x is this part here, and then you're going to have to add 2 to it as well. In the diagram we showed, our f of x is actually a negative value, right? But we still need to add 2 to it to get that amount that's left. Before we write this out, and since they're circles, there'll be pi r squared of the one minus pi r squared of the other. Technically, this is all one set of big brackets here, dx. Set up but do not evaluate. We do not need to find the answer for this. They just want to see that you understand where to put everything in. And then finally D, it can be shown that the derivative of gx is, and they give you the derivative, saving you some time. Depending on the exam, if they wanted to check if you could do that, they could ask for that. But at the end of the day, they're allocating a certain amount of marks. And in this question, they're like, we don't want to check if you know how to do that. We'll assume you can. There's your derivative. Find the value of x between 0 and 1, at which the line tangent to the graph of f is parallel to the line tangent to the graph of g. So what are we looking for? Okay. We're looking for, there's going to be somewhere at the same x value. Okay. So like if I pick this x value, this tangent's flat, but going straight down to this one, those two tangents are not the same at that point. The slopes are not the same at that point. You can't just say, oh, there's a point here where I have a maximum, point here is a minimum of it. It's the same, but there are different x values. We're trying to find the x value where they're both going to be the same. Okay, and it's probably, well, it's going to be somewhere in this range. From here to here, nope. And from here to here, I can actually erase this part. It's got to be somewhere in there. Because that's the only places where the slopes of both are positive. Yes.
It says it has to be from 0.
Oh, from 0. Oh, then it's going to be somewhere. Thank you. It's going to be from 0 to 1. I can take up my green pen. Here is where they're both negative. It's got to be somewhere in that section where both slopes are negative. Obviously, it's not going to be in the place where one is positive and one is negative. So we can find our derivative for f really easily. This is kind of nice. They would give you a mark for that on the exam. And you're like, yay. So even if you're stuck on the question and say to yourself, I don't know how to do it all, do what you can because there's marks allocated for those things. So finding that derivative for f prime is no problem. Now what do we need? We need those two to be the same. And we have a calculator. So I would take this, I'd put this into y1, I'd put this into y2, and I'd figure out where they are equal to each other. All right, I'm going to play around with my calculator a little bit here, see if it likes this. So I'm asking my calculator to find the derivative with respect to x of alpha y2 So what I'm saying in y3 here and y4 is find the derivative of y1, evaluate it at all values of x. Find the derivative of y2, evaluate it at all values of x. And did you know on your graphing calculator that if you go to the equal signs and push enter, you can turn on graphs and turn off graphs? So if I unhighlight these equal signs, it's not going to regraph f of x and g of x again. Now when I push enter and graph, I'm hoping that it's just graphing my derivatives. Isn't that cool? And where do I want it? Between 0 and 1. So I want to calculate the intersection here, number 5. And if you move your cursor, because there's 3 intersection points, but if you move your cursor closest to the one you want to find, it finds that intersect at 0.0657, 75675, and then round it. Did I read it wrong? Just. Oops. There we go. Yeah, 0.676. There we go. Kind of neat calculator tricks, eh? That you can use. So that derivative button, if you say x equals 3, it finds you the derivative right at 3. But if you write x equals x, it will graph them all. And if I go back to my graphing calculator, right, I can go back to those equations. I can turn these ones back on, which gets a little bit busy there. Okay. I'm going to, even though it's super, wow. So according to this, at that point, on my blue graph, I have a slope like that. And on my red graph, no, not my red one. Yeah, my red graph at that same value. If I draw them in, apparently those slopes are the same. It's a little busy though. That's why it was nice to highlight certain graphs, or you can zoom in. Because right now, with everything that happened there, it's a little bit busy. Okay. Question number 2. An invasive species of plant appears. Oh. Okay.
One second.
Yeah, for sure.
For quiz 3, I put the answers in teams.
An invasive species of plant appears in a fruit grove at time t equals 0 and begins to spread. Oh no. The function c divided by c of t, got an arctan, models the number of acres in the fruit grove affected by the species t weeks after the species appear. It can be shown that the derivative is there. Okay? So, obviously during the year, we had some functions we dealt with way more, and you're way better at with your derivatives. Okay? But they will be testing all of your derivatives, so make sure you know your derivative of your arctan, sine inverse, cos inverse, know all of your integrals. That's something that the ones that you struggle with, we had that purple sheet that had all of them on there, right? Take that with you on the bus if you're traveling by bus and just like, okay, can I go through the ones that I'm struggling with a little bit? It's nice that they remind you that you should be in range. I like it. Find the average number of acres affected. So we see this average number, and our head starts to think about averages and all the thing we've done with averages. Okay. From time t to time equals 4 weeks. Show the setup in your calculation. So what is the average of a function? Okay. So if they ask the average of something you have the equation of, then you can use the average of the function formula. If they ask you an average and they give you not the equation, then you might be able to use the secant one. Okay? So for example, when I'm thinking of averages, I often think about distance, speed, and time graphs. If I give you a displacement or a distance function, and I ask you for the average speed, well then you just would take the total distance you traveled over the total time, and that's the slope of the secant line. Notice I'm asking the average speed, but I gave you the displacement or distance function. Okay? If I ask you an average here, they ask average number of acres, and we have this function is the number of acres. Now that's average of a function. It's not a secant line because you have the function, so then we use 1 over the distance and then the integral from 0 to 4. And again, would make sense to type this into our calculator into y1. Notice, write C of t there. Don't write all that, 7.6 arctan 0.2 t. It wouldn't take you super long, but it saves you a little bit of time. It's also very hard to make a copying mistake down if you write C of t. Find the time when the instantaneous rate of change is the derivative, right? Instantaneous rate of change equals the average rate of change of C over the time. Okay, so now we've got average rate of change, instantaneous rate of change. So the average rate here would be the secant line. Because this is like they gave you the distance formula. They wanted to find average speed. Now it's the secant line. So we can just take C of 4 minus C of 0 over 4 minus 0. That would be the average rate. C prime of t needs to equal that. So again, I'm going to take, while you're writing this down, I'm going to take my graphing calculator out. I'm going to put these things in just to show our skills with the calculator, because copying this down is all fine and dandy, except if you don't know how to do it. So I'm going to just... Everybody know that arctan is tan inverse. All right, so in my graphing calculator, in y1, I put the tan inverse graph, and in y2, I put the derivative. They were both given to me. I'm like, this might be helpful. So in A, I figured this out. I can just redo that calculation. So I can go second quit. I want to find 1 divided by 4 of the integral from 0 to 4. And I put the regular function into y1. So there's my 2.778. Then in B, here I've got this value, so I'm going to do that on my calculator as well. And remind you that you can do y1 of 4 minus y1 at 0, all divided by 4, to get that value of 1.282. I might need all those values, so I'm going to store this as A. And I'm going to go to my y equals and graph that as well. So what am I really curious? I'm curious when this A value equals my derivative. So temporarily, I'm going to turn off the equal sign on my first graph just so that I can just see the derivative and just see my equation. I want to find the intersection point, so I'm going to calculate where they intersect. I'll move a little bit more so I'm towards the positive area. and I get 2.154. Okay, again, we're going to need, it's a word problem. They're going to be looking, do you have the right units? So I will make sure that I write weeks in there because the original question says that things are based on weeks. Assume that the invasive species continues to spread according to the model for all times greater than 0. Write a limit expression that describes the end behavior of the rate of change in the number of acres affected by the species and evaluate this limit. So our limit's going to go to infinity, and we're going to want to find the limit as it goes to infinity of that rate of change, because it's the end behavior of the rate of change. So end behavior would be at infinity, and there's our rate of change. And again, C prime of t, what happens is t goes to infinity of that, the bottom of that fraction would get huge, which makes it go to 0. So that's not something we needed our calculator for. We could figure that out just with regular limit laws and our ideas of limits. At time equals 4 weeks after the invasive species appears in the fruit groves, measures are taken to counter the spread of the species. A function a, defined as this, and notice that a is an accumulation function, where we've got C of t, which is the invasive species, and then you're going to subtract, and from time 4 on, this is how many things are taken out. At what time between 4 and 36 does A attain its maximum value? So, what does this make you think of? EVT, extreme value theorem. Okay. Where is it going to attain its maximum by the extreme value theorem? Either at the endpoints or at any critical points. So to find our critical points, we're going to have to find the derivative and set that equal to 0. So finding the derivative of this is the fundamental theorem of calculus part 1. This part just becomes 0.1 t, natural log of t. Set that equal to 0. And again, you could graph this, plug this in, and you could store this value as b, because we already had a value stored as a in this question. Okay. And it wouldn't be bad in here. Write out that since the function is continuous, we can use the extreme value theorem. So for all of your extreme value, intermediate value, mean value theorem, you need to state the conditions in order to use it. So here are our candidate points. We've got our endpoints and our one critical point. We look at all three of those values. And this is how you would calculate each of those. And then a statement to say that the max area happens at 11.442 weeks.